Hello, everybody. Welcome back to Engineering Mechanics. In this session, we are going to discuss about two-dimensional particle equilibrium. This is a very important material for all engineers. Whether you are going to be a mechanical engineer, civil engineer, aerospace engineer, it really doesn't matter. The principle that you are going to learn in this class are going to be subsequently used in every single class. So please make sure you master the principles that you are going to learn in this class. Now, I use the words two-dimensional particle equilibrium. The word two-dimensional makes sense to you already, meaning we are going to work on problems that are on a plane. That's two-dimensional. Let me briefly talk about particle. What do I mean by particle? Particle is an assumption that we make in this class to make our life easier, making problem solving simpler. Let me give you an example. In real life, we deal with, say, cars. Cars are actually not particles. They are large objects. They have certain size. They have certain shape. But let's say if you are dealing with a bridge. I'll give you an example. Golden Gate Bridge, George Washington Bridge. Say if you are involved in analyzing this bridge, then you are interested in knowing the live weight on these bridges. And when I say that, we are very interested in knowing the vehicles that are on that bridge. Now, it really doesn't matter whether you are driving a Corolla or a BMW. What is important is the weight of that vehicle. That's what matters. So if you are doing a bridge analysis, we are interested in a particle. We are not interested in a particular type of a car. We are not interested in its size. We are not interested in its shape. We are just interested in its weight. So in this case, a particle assumption makes our life easier. So a particle is really a concentrated mass. I want you to make sure you understand this. A particle means a concentrated mass. We are going to ignore all the shape sizes. It is kind of represented by a dot. That's particle assumption. The next term that I used in two-dimensional particle equilibrium is the word equilibrium. What is equilibrium? Equilibrium is kind of a scenario where all the forces acting on a body are balanced out. What do I mean by that? If you look at a stationary object, such as a table or a chair, that object is in equilibrium because nothing is going on. But I want you to understand something very clearly. When we say equilibrium, forces are balanced out. It is not the absence of forces. Forces are still there. All right? Now, I also don't want you to get the impression that equilibrium means bodies are stationary. Of course, stationary bodies are in equilibrium. But bodies can move. Imagine a plane. While it is taking off, it is not in equilibrium because forces are not balanced out. It is taking off. It is accelerating. Similarly, a plane landing is not in equilibrium. On the other hand, you could imagine a plane under the conditions of equilibrium if it is having a steady flight at maybe 30,000, 40,000 feet high, and it is a nice day, there is no turbulence, and the plane is at 400 miles an hour. Now, in that case, you can say we can apply the conditions of equilibrium for the plane because it is not accelerating. So equilibrium means particles are not accelerating, meaning forces are balanced out. I hope you understand that. With that, we are going to solve a problem. But in order to solve the problem, I also want to talk a little bit about ropes and cables that we will be using in this particular problem. Ropes, cables are widely used in our everyday life. You use them to tie things down, to carry things, but they are also widely used in engineering. You can look at these huge cranes. They use cables. Look at suspension bridges. They use steel cables. So cables are widely used. And one thing if you have to know about cables, it is this. Cables work only under tension. They do not take compressive load. So anytime you see cables or ropes in any of your problems, you immediately know the forces are tensile. We are dealing with tension. With this in mind, understanding what is a particle, understanding the concept of equilibrium, let us turn our attention to a particular problem. This particular problem is taken from a popular textbook. Let's take a look at this problem and solve it. All right, everybody, let's solve this problem. As I mentioned, this problem is from a popular textbook, Beer and Johnston. A very simple problem, and it is good for us to solve a simple problem as we get started. Then we'll move on to more complex problems. So let's take a look at this one. What is given to us? Here is a crate, and the mass of the crate is given to us. And these two guys are trying to lift it using a cable and a pulley system. And our task is to find the tension in the cables. You know already the cables are always in tension. And the tension in this cable is known because that will be the weight of this. Or we want to find the tension in these two cables, cable AC and cable AB. So how do we solve this problem? I would like you to follow a step-by-step process. This is a very important process because if you adapt a step-by-step approach, you can solve any complex problem and it is going to be easy for you. The first step is identifying the area of interest. What is the area of interest for us here? Take a look at the problem. We have three cables and they are concurrent because they intersect at point A. So my interest is this area because in this area, all three cables come together. When all three cables come together, I know the tension in one of the cables and I need to find the other two. So I am going to isolate this area. And this particular process is known as drawing a free body diagram. Let me write the acronym for free body diagram, FBD. You're going to hear this word again and again and again in this class. Drawing a free body diagram. What is a free body diagram? Free body diagram is a mathematical representation of a real problem. What you just now saw is a physical problem with pictures, people, truck, and everything. But in reality, you don't need any of these for solving the problem. For solving this problem, you just need those three cables. All right? So you want to free the area of interest from everything else. That's the first step, drawing the free body diagram. I'm going to walk you through a step-by-step process in drawing the free body diagram. Free body diagram essentially is a mathematical model, all right? And it must have all the information for solving the problem. So let's draw the free body diagram first, and then we will write the equations, and then we'll solve them, all right? So, drawing the free body diagram. Step number 1, identify the area. Isolate the area of interest. And then we are going to draw a sketch of that area. So what I'm going to do is I'm going to take another piece of paper, all right, and draw the sketch of this area. Since you know how this one looks like, I'm just going to take that off. This is how those three cables look like, all right? These are all the three cables. So I have isolated and I have drawn a sketch, but this is not complete. What we need to do now is to show all the forces. What are the forces? Well, you know the weight is acting. That's going to be the weight. All right? Then there is going to be tension in this cable and tension in this cable. So after drawing the sketch, show all the forces. I have three forces. I have shown all the forces. And then it's very important you label the forces. A free body diagram is not complete if you do not have all the forces labeled. In my class, if your free body diagram is missing a force or an important information, you will not get any credit. Because with an incomplete free body diagram, we cannot write correct equations. If you cannot write correct equation, then you will not get the proper answer. So it's very important you show everything. So I have shown all the forces. I'm going to label the forces. We know there's going to be tension in this cable, so I'm going to say tension in cable AC. And this cable is tension in cable AB. Since it is tension, I'm going to show T, but you could use any notation you want. So after showing all the forces, next step is I want to identify all important critical information necessary for writing the equation. In this case, the information that is necessary is this angle, which is 30 degrees. We also need this angle, which is 50 degrees. So I have shown all essential information. All right. Forces are here. Dimensions or the angles are here. And the last piece of information that is important is to attach a coordinate system. Well, in this case, I'm going to use a simple coordinate system, x along this and y along this. This is a complete free body diagram. Again, steps in drawing free body diagram. Isolate the area of interest, draw a sketch, show all the forces, label all the forces, show all critical information, attach a coordinate system. You will be able to download a handout from the website showing all the steps. Now that I have my free body diagram, I am ready to write my equations. Take a look at the forces here. We have TAB unknown, TAC unknown. We need to find them. But we know the weight. Well, we actually know the mass given to us 75 kilogram, and you know how to calculate the weight. Weight is equal to mg. So I'm going to take the 75 kilogram multiplied by 9.81, and I'm going to get my weight, which is going to be, I believe, 736 Newton. All right. So this weight is 736 Newton and it is known. All right. So next step is I need to write the equations. Let's write the equations. Now, all of you know this is static equilibrium, meaning sum of all the forces should be equal to 0. In this case, there are three forces: weight, tension in cable AC, tension in cable AB equal to 0. As you can see, this is the vector equation, and each vector equation in 2 dimension has got 2 scalar equations. So let's write those scalar equations starting with sum of the forces along x-axis equal to 0. I'm going to start with force in cable AC, which is tension AC, and I want to find the x component of that. As you know, in order to find the x component, all I have to do is to project this axis, all right? Project this force onto this axis. So I get this component. This is my x component. And that x component can be obtained using simple trigonometry, TAC times cosine 30 degree. I hope it makes sense to all of you. It's pretty straightforward. And move on to the next force, TAB. I want to project onto the x-axis again. As you can see, here is the component, and this is in the negative direction of x, so minus TAB. And again, since this is 50 degree, this is going to be cosine of that, so cosine 50 degree. So x component of TAC, x component of TAB, and as you can see, there is no x component of weight, so there is nothing else going on, so this is going to be equal to 0, and that's my first equation. Realize this is one equation with 2 unknowns. Clearly, we need one more equation to solve this, and that we can do by summing up the forces along y-axis. So sum of all the forces along y-axis is equal to 0, and I typically start with the same force, so there is no confusion. So let's go to TAC. Instead of x, I want the y component. And again, you are looking at a triangle like this. This is my component. This is going to be my y component. And this is my angle 30 degree. So y component can be obtained by using sine angle. So it's going to be sine 30 degree. And that's going to be positive because it is going up. Then let's move on to the next force, TAB. And again, if you look at it, it is going to be sine of 50 and it is going up in the positive y direction. So I'm going to put positive TAB sine 50 degree. And I'm done with that. And the last force left is W, which is the weight, which we know as 736 Newton. And it is a known quantity. And it is in the negative direction. So I should say negative 736 equal to 0. But I'm going to take it to the right side. So it becomes positive 736. And this will be my second equation. So these are all the 2 equations that I have developed. In these two equations, we have two unknowns, which is TAC and TAB. Two equations, two unknowns, and it can be easily solved using any approach. Some of you may like to use a substitution approach. Please be my guest and use whatever approach you want to use. Having said that, this is a simple problem. But when we go into 3D particle equilibrium, you will be dealing with three equations and three unknowns. And then when we move on to 3D rigid body equilibrium, you will be dealing with 6 equations and 6 unknowns, in which case it gets a little bit harder to solve these problems by hand. Or at least it's going to take some extra time. And if you are doing a quiz or an exam, you want to be fast, in those cases, I recommend solving this problem using your calculator. In order to solve this problem using your calculator, I recommend a matrix approach. All you have to do is to write a coefficient matrix with the right-hand side that becomes an augmented matrix, and most calculators that you are going to be using, whether it's an HP or a TI calculator, has standard routines to solve them. So here is what I recommend. Once you develop these equations, write them in a way they are very clear and consistent, and then write down the coefficient. In this case, TAC's coefficient is cosine 30 degree. So I'm going to write this as cosine 30 degree. And then the coefficient of TAB is going to be negative cosine 50 degree. And then the right-hand side of that equation is going to be 0. Next equation, tension in cable AC is here, which is an unknown, and the coefficient is sine 30 degree. Next term, the coefficient is sine 50 degree, and the right-hand side is 736. This is your matrix. This is the coefficient. This is your right-hand side. Please figure out how to input this into your calculator. And once you input in this calculator, you are going to get two unknowns. And those two unknowns are TAC and TAB. And your calculator, in this case, if you solve it correctly, will give you an answer 480 Newton for tension in cable AC and 647 Newton in tension in cable AB. And that completes this problem. So we have distinctly done three things. We looked at a physical problem. We have drawn a free body diagram using a step-by-step approach. And then we used the free body diagram to write two equations. And then we solve. These are all the three distinct stages in solving any problem involving equilibrium. All right? I hope you will be able to follow this approach systematically and solve problems correctly.